Tactile sensing technologies have drawn significant attention as they offer robots the ability to emulate human-like sense of touch. This heightened interest is attributed to vision-based tactile sensors' ability to provide high spatial resolution measurements with minimal instrumentation. Vision-based tactile sensors involve an imaging sensor observing a set of markers on an elastomer surface. Upon contact, the deformed marker configuration is utilized to infer tactile measurements. Consequently, vision-based tactile sensing algorithms witnessed remarkable advancements and are currently developed based on simulated data, such as data developed based on finite element analysis simulations. Still, vision-based tactile sensing technologies are limited by the limitations of conventional cameras, which include high latency and low temporal resolution. Neuromorphic vision sensors are bio-inspired imaging instruments that address these limitations with their asynchronous nature. This visualization compares the output of neuromorphic cameras to conventional cameras with both sensors observing a rotating dot. The neuromorphic vision sensor fires sparse asynchronous events upon relative motion, unlike standard cameras which generate synchronous frames. These unprecedented capabilities inspired neuromorphic vision-based tactile sensors. Yet, the output of the neuromorphic vision sensor is asynchronous, unlike standard cameras. This implies that traditional Sim2Real transfer frameworks for vision-based tactile sensors are not directly applicable for neuromorphic vision-based tactile sensors. Consequently, current neuromorphic vision-based tactile sensing algorithms require data collection setups that are costly, complex, and such data collection approach remains time-consuming. To address this gap, we propose, and for the first time, NeuTac, a zero-shot Sim2Real transfer framework for neuromorphic vision-based tactile sensors. NeuTac introduces a lightweight neural network with a novel loss function for denoising event-time surfaces. NeuTac leverages finite element analysis simulations for simulating the neuromorphic tactile sensor, and during real-time experiments, features are extracted as neuromorphic vision-based measurements that are correlated with the simulated data. The proposed framework relies on two key components. First, the raw event stream received from the neuromorphic vision sensor is converted to an event-time surface image-like representation. In order to ensure robust extraction of neuromorphic vision-based measurements, the event-time surface images need to be denoised for high detection success rate of the markers and tactile perception with high accuracy. Thus, the time surface images are fed to a lightweight neural network with a novel loss function for unsupervised denoising. After denoising the time surface images, the markers are extracted with a blob detector. The detected marker centers are our neuromorphic vision-based measurements and are correlated with FEA simulated data. Second, the tactile sensor is simulated in FEA simulation platforms. We show the application of NeuTac for contact pose estimation. The simulated vision-based measurements are utilized to train a multi-layer perceptron pose estimation model. During real-time experiments, the extracted neuromorphic vision-based measurements from the denoised time surface images correlate with the simulated measurements and are fed directly to the pose estimation MLP network. We validate NeuTac in various rigorous experiments for contact pose estimation. The experimental setup is as follows, involving the tactile sensor pressed against a flat surface using the UR10 manipulator. The experiments involve a variety of contact cases with a range of contact depths. Each contact depth case scenario includes a wide range of contact angles of 50 cases. In addition, experimental evaluation validates NeuTac based on the detection success rate of the markers, contact pose prediction accuracy, and benchmarks against state-of-the-art methods. The following experiment shows a contact case scenario for consecutive 9 mm depth increments. Our method demonstrates robust detection and tracking of the markers in which the extracted measurements are correlated with FEA-based simulated data. Experimental validation begins by evaluating the detection success rate. NeuTac shows robust detection and tracking of the markers with detection success rates exceeding 98%. In addition, the contact pose evaluation shows that NeuTac demonstrates successful Sim2Real transferrability with a pose estimation error of 0.122 mm and 0.23 degrees. We also benchmark our method against state-of-the-art methods for tactile-based contact pose and contact angle predictions. Our method demonstrates comparable performance to the state-of-the-art even when trained on simulated data while providing high update rates. We also compare the tactile perception model performance on experimental and simulated data to show the efficacy of NeuTac Sim2Real transfer.